Let us work on the past examination question today, the 2018 Paper 1, Question 10. So we first read the question. An electrical circuit comprises a power source of V volts in series with a resistance of R ohms, a capacitance of C farads, and an inductance of L henries. The current in the circuit, T seconds after turning on the power, is I amps, and the charge on the capacitor is Q coulombs. The circuit can be used by scientists to investigate resonance, to model heavily damped motion, and to tune in the radio stations on the stereo tuner. It's given that R, C, and L are constants, and that I equals 0 when T equals 0. A differential equation for the circuit is L di dt plus Ri plus Q over C equals to V, where I equals to dQ dt. Show that, under certain conditions on V which should be stated, L d2i dt square plus R di dt plus I over C equals to 0. So when we first encountered this question, we realized that it is pretty wordy and it's not entirely clear what the question is asking us for. So when we get stuck in the question, I typically recommend that we first identify which topic this question falls under. So we recall all the usual strategies we have in that certain topic. At first glance, it seems like this is a differential equation question. After all, we see the word differential equation, and we are given a differential equation, L di dt plus Ri, etc. However, if we think a bit more, we realize that the strategies and techniques we learned in the topic of differential equation doesn't quite apply here. Typically, when given a differential equation, we learn to solve it by integration and obtain the solution of I in terms of t, for example. However, that's not what this question wants. This question wants us to go from this equation that they give us to show this second equation. In particular, we want to go from di dt over here to d2i dt squared. So if we think about it a bit more, we realize that the topic this question is actually testing is differentiation. We want to differentiate to go from di dt to d2i dt squared. And moreover, because of all the terms over here, we have to use a bit of implicit differentiation. So let's try it out. We'll start by copying the question down first, of course. So we have L di dt plus Ri plus Q over C equals to V. As we've discussed just now, let's start differentiating. So let's differentiate with respect to t. L is constant, so if we differentiate this term, we get L d2i dt squared. Plus, R is constant, so we have R di dt. C is a constant, so we have plus 1 over C. Differentiation of Q gives us dQ dt equals to dV dt. So let's compare what we have versus what the question wants us to show. The first two terms actually work out perfectly, L d2i dt square and R di dt. This term doesn't look quite right, but if we observe the question did tell us that I equals dQ dt. So it does look like the question as well. The final term, however, for the show expression, we have 0. So in order to show, we need to mention that dV dt equals 0. When is dV dt equals 0? So that happens when V is a constant. And that is precisely the certain conditions which the question wants us to state. So our condition is, if V is a constant, then we have L d2i dt square plus R di dt plus 1 over C dQ dt becomes I equals to 0, which is precisely what we are asked to show. Let us proceed with the second part of the question. The question goes, it's now given that the differential equation in part 1 holds for the rest of the question. Given that I equals at e to the power minus rt over 2l is a solution of the differential equation where a is a positive constant, show that c equals to 4l over r squared. So the difficulty for this question, similar to part 1, is that it's not quite clear what we are expected to do. Once again, it sounds like a differential equation question, but that's not quite what we want. We are given a differential equation, yes, but we are not required to integrate it to find the solution. In fact, we are given the solution over here. We are given that I equals to at e power minus rt over 2l is the solution. We are not required to find it. Instead, given the solution, we hope to essentially find what c is. We hope to show that c equals to 4l over r squared. So how will we do that? What does being a solution mean? If someone tells me that x equals 2 satisfies the equation x minus 2 equals 0, it means that, oh, if I plug in x equals 2 into the solution, the left hand side and right hand side of the equation will work out, will be equal. This is similar to this question. Given that this is a solution, it means that if I was to plug in this I expression into our differential equation, the left hand side and the right hand side will be equal. In particular, it will be equal to 0 for this question. Our differential equation has derivatives. It has di dt, d2i dt squared. Our solution is I in terms of t. So in order to plug in our value of I into the differential equation, we will need to do differentiation. So this question is yet another differentiation question. We need to differentiate this solution we are given. So let's try it out. So we will start with the given expression for I. We have I equals to at minus rt e to the power of minus rt over 2l. We'll differentiate it. We have to use product rule over here. Differentiation of at gives us a, and we keep the exponential. Plus, now we leave at alone and differentiate the exponential to give us e minus rt over 2l. We chain rule multiplied by minus r over 2l. So we can proceed with further differentiation, but let's apply a simplification trick that will make our life a lot easier. And the trick goes this way. Notice we have at e minus rt over 2l. We have seen it before. That's actually over here. We have I equals to at e minus rt over 2l. So we will replace this entire expression with I, which will make our differentiation a lot simpler. So we have a e minus rt over 2l. Replace this chunk with I, plus I minus r over 2l. We now differentiate again. Differentiation of di dt gives us d2i dt squared equals to differentiation of the exponential gives us a e minus rt over 2l. Chain rule giving us minus r over 2l plus differentiation of I is di dt followed by the constants. So we now have I, di dt, and d2i dt squared, which we can sub into our given differential equation. Let's call this equation 1 and this equation 2. Let's copy our given differential equation. We have L d2i over dt squared plus r di dt plus I over c equals to 0. Let's call this equation 3. We will sub equation 1 into equation 2. Sub 1 into 3. Sorry. So we have L, replace d2i dt squared with the expression in equation 1. A e minus rt over 2l minus r over 2l. Plus di dt minus r over 2l plus r di dt plus I over c equals to 0. We'll expand this bracket over here. This L cancels with this L to give us minus AR over 2 E minus RT over 2L. Next, this L cancels with this L over here to get minus R over 2 didt plus R didt plus I over C equals to 0. These two terms can be combined. We have R minus R over 2 giving us R over 2 and didt. So we have minus AR over 2 E minus RT over 2L minus, or rather plus R over 2 di over dt plus I over C equals to 0. Let's call this equation 4. We still have di dt in our expression, so it's time to sub in equation number 2. So sub 2 into 4, we get minus AR over 2 E minus RT over 2L plus R over 2 sub in di dt A E minus RT over 2L plus minus ri over 2l plus I over c equals to 0. We'll expand. Minus ar over 2 e minus rt over 2l plus ar over 2 e minus rt over 2l. Expansion gives us a minus. Minus and plus give us a minus. R goes on top, so we have r square I over 2 times 2 gives us 4 over 4l plus I over c equals to 0. Nicely, these first two terms cancel each other out, leaving us with minus r square I over 4l plus I over c equals to 0. Factorizing out the I gives us I minus r square over 4l plus 1 over c equals to 0. Meaning that either I equals 0 or this expression equals 0. So I equals 0 or minus r square over 4l plus 1 over c equals to 0. So we have two answers, and this answer looks pretty close to what we were asked to show. So why do we have a separate answer? So notice at our first step we have I equals to at e minus rt over 2l. And we're given that a it's a positive constant. Exponentials are positive. Time, for the most part, is also positive, it's non-negative at least. So our i's for positive t's should be positive, which means that it should not be 0 all the time. So we'll reject this solution. Now we can find c. Move it over, we get 1 over c equals to r square over 4l, and c equals to 4l over r square, which is what we are required to do. Let's proceed to part 3 of our question. It goes, in the particular circuit, r equals 4, l equals 3, and c equals 0.75. Find the maximum value of I in terms of a, showing that this value is a maximum. So hopefully we'll find that this part of the question is a bit more straightforward. We recall that we have learned that to find maximum values or minimum values, we let the differential be 0. So for this particular question, we want di dt equals 0. And then we want to prove that we solve for t and I, and we want to show that this value is indeed a maximum at the end. Thankfully, we already have our expressions for di dt and d2i dt square from part 2, so we will use that in our solution. Let's try it out. Okay, so let's copy down the expression of di dt from part 2 of our solution. For part 3, we start off with di dt equals to a e minus rt over 2l minus ar over 2l t e minus rt over 2l. To simplify our working, we can immediately sub in the given values. We are given that r equals 4 and l equals 3. Notice r over 2l keeps appearing in our working, so we find r over 2l, 4 over 2 times 3, 4 over 6, which gives us 2/3. Giving us di dt equals to a e power minus 2/3 t minus 2/3 at e to the power of minus 2/3 t. Okay, so at maximum value of I, di dt is 0. This means that this expression is 0. We will factorize out the common factor a e minus 2/3 t. T, factorizing it gives us 1 minus 2/3 t equals to 0. A is a positive constant and the exponentials are positive, so we have, since a e minus 2/3 t is positive, we have this expression 1 minus 2/3 t must be equals to 0, giving us t equals to 3 over 2. Let's sub t equals 3 over 2 into our expression for I equals to a 3 over 2 e to the power of minus 2/3 t is 3 over 2, giving us 3 over 2a e to the power of minus 1. Now we need to prove that this value of I is indeed the maximum. Let's get our expression for d2i dt square that we obtained from part 2. So to d2i dt square is equals to minus AR over 2L, E minus RT over 2L, minus R over 2L, di dt. We have to simplify the expression of di dt as well. So equals to R over 2L is 2/3, so we have minus 2/3 E minus RT over 2L minus 2/3 di dt, it's over here. So di dt is A E minus 2/3 t minus 2/3 AT E minus 2/3 t. We expand. Minus 2/3 E minus RT over 2L minus 2/3 A E minus 2/3 t plus 4 over 9 AT E minus 2/3 t. Okay. So minus 2/3 E minus RT over 2L minus 2/3 A E minus 2/3 t. Here let's plug in the fact that t equals to 3 over 2. 3 over 2 times 4 over 9 gives us plus 3 over 2 gives us 2 over 3 A E minus 2/3 t. Notice that these last two terms cancel out each other. So we have minus 2/3 E minus RT over 2L. Exponentials are positive. 2/3 is positive, so a negative sign means that since d2i over dt square, it's negative, it's less than 0, we have that I is a maximum when t equals to 3 over 2. In particular, we want the max value of I, so we have max value of I equals to what we have, 3 over 2 A e to the power minus 1, and this is our solution. We finally arrive at our last part of the question. Part 4, we're asked to sketch the graph of I against t. So thankfully this part of the question is pretty straightforward, I hope, because we are already given the formula for I equals to AT E minus RT over 2L, and we can now use our graphic calculator to help us sketch this curve. Let's give it a try. So let us key our given expression for I into our graphic calculator. So in particular, I equals AT to the power E power minus RT over 2L. We can use we don't have A, but we can use any positive constant A. We can use it any value, and the graph should look pretty similar regardless of what we use. I chose A to be 2, you can choose A to be any other number. T, we use X in our graphic calculator. E to the power of, we have R over 2L is 2/3, so E to the power minus 2/3 X in our GC. Let's see the graph. So our graph goes this way. In particular, it has a maximum point, that is the turning point we found in part 3. Another interesting observation here is, as t tends to infinity, we have the graph tending towards 0. This is because when t tends to infinity, e to the power of minus infinity tends to 0. So we have an asymptote y equals 0. Or for this question, I equals 0 in particular. So we also don't need to draw the negative part for our graph because we don't have negative time for this question. So let's transfer this into our solution sheet. So we set up our axis. We have I against t. The graph starts from the origin, goes up to a turning point, comes down, and has an asymptote at the end. The asymptote is I equals to 0. We can copy the equation of our curve. I equals to AT E minus RT over 2L. In particular also, our turning point is, as we found in part 3, 3 over 2, comma, the I coordinate is 3 over 2 AE minus 1. And this graph wraps up our solution for this question.